Hello folks. Well, today finally we're going to start some programming. The way that people are usually introduced to these chips is by writing a little program that will flash a single LED. Well, to do that you have to connect the LED to one of the pins of the chip, make the voltage go up and down on that pin, and the LED flashes. But we can do a little bit better than that because we do have 5 pins available. So we can flash 6 LEDs. Here's the circuit that I propose. Here's the chip, the AT85. It's connected to 5 volts and to ground, and it has 5 legs available. And if we output 5 volts on all of these pins, then it means that, for example, this LED here, its anode will have 5 volts on, and its cathode will have 5 volts on, so the LED will be switched off. It's like connecting both ends of the LED to the positive terminal of a battery. Nothing happens. If we drop the voltage on port B4, that line there, these 3 lines are all high, so these 3 LEDs would come on. These 3 LEDs would stay off because we haven't drop the voltage on this one, only this one. If we want to light only LED 2, for example, then we can drop the voltage to 0 on port B4, and we can drop the voltage to 0 on port B0 and 2, and then we've only got 5 volts on there and 0 volts on there, so that will be the only LED lit. So with this system we can flash or we can light any LED at choice, or groups of them, or all of them. If we flash them at, let's say, 1,000 times a second, you won't see anything happening. So we're going to have to generate a delay in the chip. Now I'd just like to introduce you to the way that I got into writing delays, because I started off at the beginning of my learning curve in a very naive way. This was when I was developing the soft start mechanism for my saw, and the saw runs from 240 volt mains. So here we see a picture of the 240 volt mains, and the way that the saw works is we drive the saw through a triac. Every time the mains voltage goes through 0, the triac switches off. So you cause a delay, and then you give the triac a kick to switch it on, and it goes to mains voltage, and it follows the mains voltage until it goes to 0 again, and it switches off. And then you delay it again, and you give it a kick to switch it on, and it goes back to the mains voltage and follows it until it switches off. So if the delay is long, we only have a small amount of energy inside there and there that is delivered to the saw. If the delay is much shorter, we have a much larger amount of energy that is delivered to the saw, so you can control how quickly it starts up. And the way that it works is to alter the delay from maximum, where there's virtually no energy going to the saw, down to 0 over a period of 2 seconds. And that's how my saw delay circuit works. In order to start this delay, what we need to do is interrupt the chip every time the mains goes through the 0 voltage. I did that by taking the mains through a high value resistor and then clamping it to plus and minus 5 volts through diodes. So what I was actually looking at on the processor side of the resistor was just this red line. If we look at that in more detail, or just as the 5 volt signal, there's the red line there, and what I wanted was to generate a pulse like this every time the mains went through 0. So there was a little bit of extra circuitry around it, but yes, I was able to generate this pulse quite successfully. You've seen it working. The problem is, this is what I eventually wanted. I wanted a 5 volt pulse every time the mains goes through 0. But while I was developing this circuit, I was working with a breadboard, and I didn't want 240 volts around it, because you've got a lot of resistors standing on it with bare legs and stuff like that, and sooner or later you'll forget that 240 volts is there, and you'll get a shock from it. You'll get a belt off it. So I've had that before. I had a shock on my hand and it gave me a trigger finger, and it was so severe that there were times when I couldn't actually unbend the finger. It did eventually come right, but it took 3 years probably. So that's something that I want to avoid, really. So what I wanted was a 5-volt pulse, 10 microseconds every 10 milliseconds, and I could use that to drive the application that I was developing for the soft start. And the way that I did this was to write a routine on a separate AT85 to generate only this, and then I could use that as my pseudo mains crossing while I was developing the soft start circuit. So to get these delays, right, there's a little program. If I single step that, so F11 will compile it and go into the debugger and go to the first instruction. SBI is set bit in an IO register, and the IO register is DDRB. I think we already covered this. Load immediate R16 with a value of 3. Now at this point, just notice the stopwatch here. It's at 1 microsecond. Remember that we want to send a 10 microsecond pulse, so the pulse is about to be sent. Single step once more, and we're setting the port B. This is the pin on the chip that will raise the pulse. So we're setting that port bit 0 high. Again, the stopwatch is at 2 microseconds. When I execute that instruction, you'll see that the port has in fact gone high. This red blob, that's the pin on the chip. So it's gone high. We decrement R16. Remember that we loaded a 3 into it, so it goes to a 2, and it's there in the registers, you can see it. Branch not equals, well, it's not equal to 0, so it'll perform the branch, goes back, decrements it to 1, branch not equal, decrements it to 0. Now it'll fall through that instruction, and it'll clear the bit on the port. Now this is the port down here, so it'll clear that bit, and the pulse falls. You note that the port has a red ring around it to say that something has just happened to it. All of the others are white, but they're encircled with a blue ring. This one's got a red ring to say that it's just happened, and when I execute the next instruction, you'll see that'll go blue. The next instruction was a call to delay. So we have made the pulse. Let me do that again. So where it is beginning, there's set built. I'm going to set a breakpoint there by simply clicking in the margin. If I press F5, the program goes directly to the breakpoint, and I'm going to set another breakpoint where it unsets the bit. Now at this point we're at 2 microseconds. If we want a 10 microsecond pulse, it should be at 12 microseconds when it gets there. Press F5 again, it goes to the next breakpoint, and you see here this is at 12 microseconds, so that gives us a 10 microsecond pulse. The way that I got that was by just playing with the values. If I load a 4 into R16, it gets decremented 4 times, and it's too long. If I load a 2, it's too short. The 3 turned out just right. If it had been 1 or 2 instructions, if it had been 1 or 2 microseconds too short, I could have put a couple of no-ops in. A no-op is an instruction that doesn't actually do anything, but it does use up 1 clock cycle. So it's got down to this point here. We call the delay. Now the delay is going to be this delay here, the 10 milliseconds delay. So we'll call that delay. and it loads a value of 30 into register 20. Then it loads a value of 110 into register 21, and I got these values just by playing around with it, and if one value gave too long a delay, then I'd reduce it a bit, and just by messing around I derived these values. It took about 10 minutes. So it loads 110 into register 21, then it starts decrementing register 21 until it decrements it down to 0. When it does, it folds through this instruction there, and then it decrements register 20. Now register 20, as you see, is set to 1 easy at the moment, so it goes to 1 dog. Branch not equals, well, it's not equal to 0, so it'll do the branch back to loop 1, where it loads R21 with a 110 again and starts decrementing it again. When it's done that whole lot, it'll come down to the return instruction, and then it will return to the instruction immediately following the remote call. That jumps to pulse setup, which you can see is there. So this will load R16 with a 3 again, and it'll produce the next 10 microsecond pulse. Now if I just take that breakpoint away and I press F5, so that's gone to the point where it's about to set that pulse. If I set the stopwatch to 0 by right-clicking it and selecting Reset Stopwatch, you unfortunately can't see this drop-down box, it doesn't record, but it resets the stopwatch, and you can see there it's gone to 0. If I now press F5, it will execute all of this program, including the delay, and it'll come back to this point, and that should take it 10 milliseconds if everything is spot on. There, it's done it, and it comes back, and it's 10 milliseconds 0.012. So you can see that it's not spot on. I could make it spot on by playing with these values. I know that reducing that by 1 makes it too small, but if I mess around with these, I might be able to get it a little bit closer, or otherwise I can simply reduce it until it's less than this 10,000, and then put some no ops in, or put a small loop in, or mess around. However, I just wanted to show you that this is a way of generating a delay, and it was the first way that I thought of. But you are here to learn something about the AT85 chip. So I'm not going to use that delay mechanism this time. We want a delay of ½ a second, but the chip has some timers in it, so we might as well use them. And being as you're here to learn about the chip, this is an opportunity. So we're going to go to the data sheet. There's where the data sheet starts, the features of the chip, pin configurations, there's an overview of the chip, how the AVR core works, the AVR memories. I think we already looked at that. There's the program memory from 0 down to Fox, Fox, Fox in the case of the AT85. The program counter in the chip is 12 bits, so it can count up to Fox, 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 and the program pointer points to instructions. So it's got 4K 2-byte words. What we're looking for at the moment is the I/O ports, and we're looking for the timer. So we're going to use, we've got 2 timers with timer 0 and timer 1. We've got to use one of them, so we're going to use timer 0. Now timer 0 is going to be counted at a rate of 1 megahertz, and this is roughly what the timer is doing. There's the time counter running up from 0 up to a limit. We are going to set CTC mode, which is clear timer on compare. So every time it gets to a compare with the OCR0A, the output compare register, 0 because we're dealing with timer 0, and A because we have 2 registers. We can compare with 1 or 2 registers, and we can do different things with them. At the moment, we're just going to use one of them. We're going to use a timer running up here. Now this is counting at the moment at a rate of 1 megahertz. So it would count up to 1,000,000 in a second. The registers aren't big enough to count that high, but that's the rate of it. We don't want that to happen. We're looking for a half a second. Now there are reasons why I want to initially develop a time of 1 millisecond. The reason is that when you've got 1 millisecond, it's much easier to divide it down into half seconds than it is to divide microseconds down into half seconds. The timer can be pre-scaled, so we can use a slower clock than the 1 megahertz to clock it, and I think that seems sensible. And if you search this for pre-scal, so we'll get pre-scaler or pre-scale or pre-scaling or any of these words. The first one that we come across is from pre-scaler in the circuit diagram. And if we step through all of these, the first thing we come across is the internal clock source with pre-scaler, and we find that we can pre-scale the clock by dividing by 8 or dividing by 64 or 256 or 1024. 8 is the one that I'm going to go for. Now the reason is that we're starting off with a clock of 1,000,000 cycles per second. If we divide it by 8, it comes down to 125k. And we can easily divide 125k by 125 to get 1k, and 125 fits comfortably inside a 1-byte register. If we divide by 64 or 256 or 1024, we don't get an integral number of kilohertz. It comes down to a fractional number of kilohertz, so it becomes much more complicated to divide down. If we come down to 125 kilohertz, exactly, integral 125, then we can divide it by 125. So I'm going to divide by 8. So here's what we want. We want an interrupt every millisecond. And I'm going to set the prescaler for 8. Now we've got to find out how to do that. If we continue searching down here, prescaled, we eventually come to a table this table here. There's the I/O clock divided by 8. I'd just like to say something about the I/O clock. First of all, we're in table 11.6. I'm just going to make a copy of that so we can get back here. Section 6 is the clock options, and it shows the circuit of the clock generator. All of the clocks are generated in this block here, and we can see the CPU clock coming out there, going to the CPU core and the RAM. There is a separate clock comes out for flash, which is the program storage. There is a clock comes out for the ADC, the analog to digital converter. And there is the I/O clock, and it comes out and it powers all the I/O modules. So it's just a clock that is developed from the internal CPU clock. It's not a clock coming from outside the chip. Back to the table. So we want to divide the I/O clock by 8. So we're going to need to set these signals here, CS2, 1 and 0 to 0, 1 and 0. So CS 2, 1 and 0 gets set to 0, 1 and 0. Where do they live? Well, this shown here is actually the description of a control register. And there it is. Timer counter control register B, and the counter is 0. So timer counter register 0B. And the bits in it, there's the CS2, 0 and 1. So these go in TCC R0B. Now there is also another register, control register for this timer. and it's here, TCC R0A, timer counter control register A. Tells you what it is. The COM bits, compare match outputs. This is what to do with the pins when it gets a match output. There are three modes: compare output mode, non-pulse width modulation. We won't be using pulse width modulation, so this is the one that we'd be using. There is fast pulse width modulation, fast PWM, and there is phase correct PWM, and there are diagrams in here to show you what they mean, but we're not going to be using PWM, so this is the one we want. This is what you can do with the pins when it compares. Either you can have normal port operation, the port pins are disconnected from the timer. Otherwise, you can toggle the output pin, you can clear it, or you can set it. We don't want to do any of those things. What I want to do is to drive the pins directly from the program. So we will choose normal port operation. So the COM0A1 and COM0A0 get set to 0. So we don't need to worry about these. They're already set to 0 by default. We don't need to set them to 0. We better have a look at these WGM bits. What do they do? Well, if we look down the description here, we come to the WGM bits, and what they mean is waveform generation mode. We're not going to be generating any waveforms, although the chip can be used for that, but we're not going to. What we're going to do is we're going to set CTC mode. Remember that? CTC mode. Clear timer on compare. So every time it compares with the output compare register, it's going to clear and go down here. So we want CTC mode, which is WGM 201. And we want to set those to 0, 1, and 0. And where do they live again? They live in TCC ROA. And it's TCC R0A, not O. It's worth mentioning that WGM2 is in a different register. It's in TCC R0B, and there it is there. WGM 1 and 0 are in the register that we saw above. TCC R0A, and they're there. So the only bit that we're actually going to need to set in there is WGM 01. Now, we're not home and dry yet. You will have a program that is doing something. The timer, once you have set it up, you set the value for OCR0A. You set the, well, you haven't set anything. The timer counter is simply running up. When it reaches this value, it'll reset and start running up again. And all this just goes on in the background. You don't actually see it happening. But somehow, when it resets, you want to know about it. So what you do is you set an interrupt every time it resets. Back to the datasheet. And the interrupt is set in a different register. TIMSK. There it is, TIMSK. And the one that we want to set is this one here, OCIE0A, bit 4, OCIE0A. is the timer counter 0 output compare match A. Remember, we're using the output, we're using OCR 0A. So every time that compares, we want to enable the interrupt. So we need to set this bit on. So OCIE interrupt enable 0A, and that is in TIMSK. We're not interested in compare with B, we're not using that. Timer counter overflow, we're not interested in that, it's not going to overflow. Now the other thing that we need to set is the value of this. Remember that the counter now is counting up at a rate of 125 kilohertz because we divided 1 megahertz by 8. So when this gets up to a count of 125, that'll be in 1 millisecond. So we want to set this register here equals 125. And then once these things are all set up, the timer will simply run and it'll give us an interrupt every millisecond. Now, I've already written the program to do that. So what we do is we start off by loading the stack register. In actual fact, the chip already has the stack register loaded in the right point, but it's just good hygiene. Load the stack register and you set it to the high to RAM end in this definition file here. If you look for RAM end, there it is, and it's set to top of memory. So set the stack register. You set the high and low parts of the stack register because it's a 2-byte register. Then we load R16 with a 1 shifted left by port B0. I'd just like to explain this line. I found through bitter experience that if you take your code to a support forum like AVR Freaks, you get quite a lot of flames if you haven't used the language in the way that they use it. Now personally, I would tend just to set the direction register to 1 Fox and be done with it. However, they don't like to do it that way. They like to do it this way. First of all, PB0 by definition from the definitions file is 0, PB1 is 1, etc. 1 left shifted by PB0, in other words 1 left shifted by 0 bits, is binary 1, which is hexadecimal 1. 1 shifted left by 2 bits is binary 0010, which is hexadecimal 02, etc. You can look through you can see the 1 is getting shifted 1 more to the left each time. If you OR all of these terms together, all the zeros give 0, all the zeros give 0, 0, and any row that has a 1 in it gives a 1. So it comes out to 0001 1111, or in other words, hexadecimal 1 Fox. If you use this nomenclature, you're more likely to get a sympathetic hearing if you need to take your code to a forum to ask questions about it. So you put this into register 16 first, and then you do an output of register 16 into the direction register. If we single step that, we can see it happen. Load R16. R16 is done here, and when we load it, single step it by pressing F11, and all of those bits go in, and it's one FOX. Now we output that to the direction register. If we open this up here, we see the port registers. Each port, we only have port B on this chip, but the port has 3 registers concerned with it. So there's the pin register, which handles the inputs. There's the direction register, which handles whether each pin is output or input. And then there's the port B, which is the actual value of it. So when we put this into the direction register, F11 to single step, and there you can see the directions are outputs for these 5 bits. Now, going back to our requirements, we want to prescale the clock by 8, which involves setting CS210 to 010. So effectively CS1 has to be set. So the first thing we want to do then is set CS1 there into R16, which is a general purpose register, and then we move that to TCC R0B. The next thing we want to do is set CTC mode, which means set WGM01. So we set 1 shifted by WGM01 into register 16, and then move that into TCC R0A. The other thing we want to do is enable the interrupts. So we set a 1 shifted by this and OCIE0A. If you look in there, OCIE0A, there it is a 4. So that 1 will be shifted 4 places, setting the right bit in this register. So will it all work at that point? Well, no, not quite. We will have the counter now running up, being compared with 125, coming back to 0, but we won't be getting an interrupt at this point, although we have enabled the interrupts, but we have to enable interrupts on the chip globally, and the instruction to do that is that set enable interrupts. So once that gets done, we should see the chip counting up. If we just set a label, compile that now, set the stack pointer, set the directions, and there we see in the IO register the directions being set. We load CS1 into register 16, and there we see it's got a value of 2 now down there. I'm not going to keep pointing to the registers all the time. You can see where they are. It loads WGM1 into register 16, which is also a value of 2. And it outputs that to TCC R0A. Now this is in timer counter 0. Which is this one. TCC R0A is here. So when it loads it in, there we see that bit has been set. And it's when I hover on this, it tells me what it is. Unfortunately, it doesn't get copied to the video, but it says WGM0. We now load R16 with that value. We send it to TIMSK to enable the interrupt, and there we see TIMSK. That bit has been enabled. We haven't yet set the 125. So we need to set that. So now we're in a position to be able to test this program. If I single step it, it loads the stack register, it loads all of those things into the direction register, it sets up all the stuff that we've been doing, it gets down to the bottom, it sets the global interrupt, and then it sits here just jumping to itself at that location. But while it's jumping to itself, it's generating clock cycles. If we now look at the timer, timer 0 is that one, and we keep on pressing F11, now you see the red blob there. TCNT0 is the timer counter 0, so that's the actual count that it's got in. And if we keep on pressing 11, we can see that it's going up. It's increasing. Now it's got to climb up to a value of the value in OCR 0A, which is 7D, 7 dog. Now if I've got to keep pressing F11, remember I've got to press it 4 times. 2, 3, 4. For each time it counts, because we're dividing the clock by 8. The instruction we're doing is an R jump, which is a 2 clock cycle instruction. So every time I press it is 2 clock cycles, but we need to press it 8 clock cycles for it to count once. So that's 4 presses. Now if we've got to wait for this to climb all the way up to 7 dog, that's going to take quite a long time, so we don't need to do that. We can set it here. If I click that, click that, click that, there it says 7 Baker, and if I put another couple of counts into it, there's 7 Charlie, 7 dog. So now 7 dog, it has reached this value. It won't go above that. There, it has reset back to 0. So that seems to be working. But it's not really very useful yet. The screen is reflecting in my glasses. I'm sorry, there's not much I can do about that. The next part of this tutorial will be much shorter, and I'll show you the vector table. We'll write a little interrupt to handle the routine that we did today. We'll set flags in a flag register to control the counters, and I'll show you how to get your program from your computer into the chip. And I would like to apologize if this has been long and tedious, and I'm sorry if you're expecting a thrill ride, but microprocessor program is not an emotionally charged subject. Anyway, look on the bright side. What you've covered in 40 minutes took me many weeks to learn. So, see you next time.